All right, so hopefully everybody got to take the quiz. Right now, I'm not exactly sure what the difficulty level is, whether it's medium or hard. It's definitely not easy. Once I get more data, I'll update the YouTube title so that we know what this is. Okay, so this is the first question. In my mind, there's three ways to approach this. So, number one, you can approach this using kind of conceptual knowledge. And this is going to be the most confident way to do the problem. Number two, you can choose numbers. So this is going to be the most strategic way to do the problem. And number three, you can try to approach it using algebra, which I think is going to come across as the most cumbersome and the most unwieldy. So first of all, let's do it as conceptual. So first of all, what do we see? The least common multiple of three consecutive integers, the least of which is odd. So if we have three consecutive integers and the smallest one is odd, we know the first number is odd, the second number is even, and the third number is odd. If your conceptual knowledge is really strong, you will know that these three numbers share no factor other than 1. They only share 1 as a factor. They don't share any other factors whatsoever. The reason why that's important is because whenever that happens, the LCM is literally just the product of the three numbers. So that would be C. So that's the conceptual approach. That's the maybe the fastest approach, but it's also the approach that, in a sense, is the most dangerous because you're not doing any work to verify it. So you have to be very confident about your approach, right? Okay, so that is the conceptual approach. Choosing numbers, well, obviously, you just start with like 1, 2, 3, right? So 1, 2, 3. What is the product of these three integers? 6. What is their LCM? 6. And then you can verify it with, the next case, 3, 4, 5. What is the LCM? It's going to be 60. What is the product? It's going to be 60. And if you really want to, you can even confirm it with a negative number as well. So -1, 0, and 1. What is the LCM? The LCM is going to be 0. Well, I guess, does this even make sense when we use negative numbers? Yeah, maybe not. Maybe it doesn't make sense. I don't think GRE is going to ask an LCM question with negative numbers. Yeah, so if you want to confirm it with 5, 6, and 7, you'll see that it all works out. Now, if you want to do the algebra, this is where things get really messy because you're going to say, okay, the first integer is x, the next integer is x plus 1, the next integer is x plus 2, and then you multiply them all together and you get this weird cubic. Yeah, I don't recommend the algebra unless I'm just completely missing something. Me personally, I would solve it either using method number 1 or method number 2. That's how I would approach this one. So the correct answer is C. Now, that's not to say that my approach is the best approach. I'm just telling you how I would approach it. I would approach it either with number 1 or number 2. All right, so that is the first problem. Let's move on to the second problem. So here's the second problem. There are 3 identically sized marbles in a bag, 1 green, 1 blue, and 1 red. John is randomly pulling the marbles out one by one without replacement. So taking a marble out and leaving it out. This is where conceptual shit can really backfire. It can really bite you in the ass because let's say you try to solve this conceptually and you're like, well, of course, the probability of pulling out the red marble second is going to be higher than the probability that John pulls out the red marble third. So from a quote, conceptual, unquote, point of view, you'll say the answer is A. But no, probability is not very intuitive. Sometimes it does some weird shit. I mean, just look at the Monty Hall problem. If you want to Google that, you can see how weird probability can get, or the birthday paradox. So because there's only 3 marbles, green, blue, and red, I would recommend just brute forcing it, writing out every single possibility. So we could choose the green one first, the blue one second, the red one third. We could choose the green one first, the red one second, the blue one third. We could choose the blue one first, the red one second, the green one third, the blue one first, the green one second, the red one third. And you might think, wow, this is tedious as hell. Not really, because there's only 2 more. We could choose the red one first, the blue one second, and then green, and then red, green, and then finally blue. So these are the 6 possibilities. So what's the probability that the red marble is second? Well, we have 6 total possibilities. 1, 2, 3, 4, 5, and 6. We have 6 total possibilities, but notice the red one is in 2 of them, where the red one is second. Okay, so the probability must be 2 out of 6. Same thing with the third one. Notice how the red one is in the third position twice. So that's also 2 out of 6. So the correct answer is C. What makes this really crazy is that it's true even if there's like 100 marbles. So for example, the probability of pulling out a red marble first is the same as pulling out the red marble 99th, even if it's with replacement or without replacement. I told you probability can be sometimes counterintuitive. That's why I tried to make this one a little bit easier by having only 3 marbles so that you could brute force it. All right, so that is question number 2. Question number 3, the number of times the line y equals 3x plus 3 intersects this parabola. And the formatting's a little bit odd. I apologize about that. So whenever we want to find intersection points, what that means is we have a set of points, x, y, which if we plug those into both equations, they both work. They both work, right? So the easiest way to solve this is to set these two equations equal to each other. So we could say, for example, y equals y, but that's not very helpful. So instead, we're going to say, okay, in the first equation, y equals 3x plus 3. In the second equation, it equals negative x squared plus 4x, and then minus 7. So what we have here is a quadratic in non-simplified form. So what we want to do is move everything over to one side. I personally don't like dealing with negative Nancy's, so I'm going to move the x squared over here. So we have x squared, and then minus 4x, and then the plus 3x, so that's going to be a minus x. And then if we plus 7 to both sides, we're going to get plus 10 over here. And of course, that equals 0. Now, typically, what I recommend people to do when looking at a quadratic is first ask yourself, can it be factored? In this case, I don't think there's a clean factor happening. So what we want to do is we want to use the quadratic formula. And the quadratic formula is pretty nasty. It's going to be negative b plus or minus, and then they have this big square root, b squared minus 4ac all over 2a. Now here's the good news. So the bad news is this is some ugly crap. The good news is we only need this part, b squared minus 4ac, because it presents 3 possibilities. If b squared minus 4ac is positive, we're going to be adding a positive and subtracting a positive number, which is going to result in 2 solutions. And 2 solutions means 2 intersection points. However, if this equals 0, b squared minus 4ac equals 0, notice we're doing negative b plus 0, negative b minus 0. That's the same thing. So that's only going to be 1 solution. However, if this is negative, you cannot take the square root of a negative. That's invalid. So this is going to be 0 solutions. So we just have to do the b squared minus 4ac part. So what is b? B is going to be negative 1. We square it. Obviously, we get 1. And then minus 4ac. A is 1. C is 10. So 4 times 1 times 10 is 40. And that's going to equal negative 39. So what we're doing here is we're taking the square root of negative 39. That's not going to work. So this is going to have 0 solutions, 0 intersection points, which means quantity B is bigger. Correct answer is B. So that is number 3. Let's move on to number 4. 2 sets of data, A and B, are normally distributed with median x and standard deviations larger than 3. When graphed, the bell curve of set A is taller than that of B. So we should probably look at this, or at least try to draw it, but my drawing is such ass that I'm going to pause this recording and find a picture. Hold on one sec. All right, I know I'm covering up the answer choices a little bit, but we have the graphic. Let's take a look. So we have two sets of data, A and B. Which one is taller? So A is taller. So let's take a look at A. So this is A and this is B. Now, whenever they have the same center, we know that if we were to draw a line right in the middle, it would intersect the middle of both of these. So what that means is they have the same median and the same average, roughly, because it's normally distributed. However, the standard deviation is not the same in these two. Remember, standard deviation is how spread out it is, So if we look at if we look at graph B, notice how it's wider, like it's more spread out. So what that means is the standard deviation of B is bigger than the standard deviation of A. Now, the reason why this is important, it's because if we're starting in the middle of both of these charts, and we're saying the middle to x minus 1 to x, we're going to subtract it a little bit, right? So let's go ahead and just like draw a line like right here, for example. So let's imagine this is x minus 1. Okay, let's just imagine. The question is, where are we capturing more data? Are we capturing more data in A, the tall, skinny one, or in B? Well, let's look at it. In B, so this is for B, this is the data we're capturing. But notice we still have a lot of room here. We got B's over here, it's way over here. So we're capturing only a pretty small portion of it. But if you look at A, if we keep going like all the way up, we're capturing almost half of A. I mean, like, look, there's this little part over here and obviously to the right, but we're capturing more percentage of the data. So that's why the correct answer is going to be A. This is a conceptual problem, but I do think drawing these would illustrate more easily what's going on. If you have a really good conceptual understanding of how standard deviation works with normal distribution, you might not have to draw the graph, but I would recommend for most people drawing the graph, making sure you understand what it means. In a nutshell, if you have a smaller standard deviation and you move away from the mean either up or down, you're going to capture more data, a larger percentage of the data, because the standard deviation is small, which means it's tall and skinny, right? If the standard deviation is bigger, it's going to be wide and kind of flat. And in that case, if you move to the left or to the right of the median, you're not going to be capturing as much of a percentage of the data. Now, somebody asked a really good question. How come we can't have a chart that is both wide and tall? So for example, why can't I have this B chart be all the way up to the A point, but also be the same width? The reason being is that the area under the curve, so the area under the curve of every normal distribution chart equals 1. So what that means is if I was to move the B one all the way up to here, but keep the same width, the area would be much bigger than 1. And the reason why 1, of course, is because remember, these give probabilities, they give percentages. If you add up all of the possible percentages, what do you get? You get 100%, right? And if we're writing 100% as 1, well, it's the same thing, right? You can even think of it as probabilities as well. Add up all of the probabilities that are possible, what do you get? You get 1. So that's why the area under the curve has to equal 1. Okay, so the correct answer is A. So that's question number 4. Let's go ahead and move on to question number 5. A person starts at 10 on a large number line and wants to land exactly on 30. This person can jump any distance they like. However, they must follow these 2 rules. They can only land on whole numbers. Every jump must be the same size. And of course, we're assuming you can only go forward, no backward jumps here. In fact, I should probably clarify that in the question. All right, if you take this quiz after this recording, you'll probably see a slight wording change. So this is a really good opportunity to use a strategy which is called create an easier example. It's a very good opportunity, right? So instead of saying 10 to 30, why don't we say 10 to 12, right? So isn't there 2 possibilities? So possibility number 1 is I just take 1 jump of +2. So that's just 1 jump. Possibility number 2 is I take a jump of 1, but I have to do 2 of those, right? So 10 to 11 and then 11 to 12. So notice what we have here. We have 2 and 1 when we're going from 10 to 12. Okay, interesting. Let's now try 10 to 13. Well, the first case would be a +3 jump, which would only be 1. The second case would be, again, the +1 jumps, which I would have to take 3 of those, right? So again, we have 3 and 1 whenever we're going from 10 to 13. Do you see the pattern or not yet? Maybe you don't. Okay, let's do another example. Let's imagine we're going from 10 to, let's say, 16. So we could do the big jump of +6. We could do the small jumps of +1, right? So 11, 12, 13. We could do jumps of 2. So we could go 10 to 12, 12 to 14, 14 to 16. Or we could even do jumps of +3, 10 to 13 and 13 to 16. Do you see the pattern? So notice if we were to do 16 minus 10, we get 6. What are the factors of 6? The factors of 6 are 6, 1, 2, and 3. Ooh. If we go 12 minus 10, we get 2, right? What are the factors of 2? 2 and 1. If we do 13 minus 10, we get 3. What are the factors of 3? 3 and 1. Ooh. So what we need to do is we need to do 30 minus 10, which equals 20, and find the factors of 20. That's the answer. So the factors of 20, what are they? Let's use the nifty factor finding system. So 1 times 20, 2 times 10, 4 times 5. So that's called the nifty factor finding system. If you're interested in that, you can check it out on PrepSwift. So 1 times 20, 2 times 10, 4 times 5. How many factors is that? That's going to be 6 factors. So what's bigger, 6 or 8? Obviously 8 is bigger, so B is the correct answer. So those are the 5 quantitative comparison questions. Remember, whenever we do a Section 2 quiz or a Section 2 section on the GRE Quant, it's going to have 15 questions, 5 of which are QC. All right, so there we go. Let's now move on to number 6. Yeah, let's move on to number 6. Does 20 have only 6 factors? Let me double check. 1 times 20, 2 times 10, 4 times 5. Yeah, I don't think I'm missing anything. That's kind of the beauty of the nifty factor finding system. It really allows you to capture all the factors without making a silly error. Number 6, if X is 2/3 larger than Y, then Y is what % smaller than X? Again, you can approach this in multiple ways. Probably the easiest way, in my opinion, would be choosing numbers. So the mistake most people make here is they assume that X is smaller than Y. They say, oh, X is 2/3 smaller than Y, or 2/3 of Y. So for example, if I say that Y equals 12, X is going to equal 2/3 of that, which is 8. But that doesn't make any sense because it says that X is larger than Y. And if X is larger than Y, something's wrong here. We made a mistake. This is what we would call a silly error, right? A careless mistake. So X has to be 2/3 larger than Y. So let's imagine, for example, that Y equals, let's say, 9, right? Y equals 9. If X is 2/3 larger than Y, well, first of all, what is 2/3 of Y? That's 6, right? And so then we do 9 plus 6 and we get 15. And so now we can solve the problem. So Y is what % smaller than X? Remember the % decrease formula. So the % decrease formula, you find the change or the difference between the two numbers, right? And you put that over the larger number. So this is how we find % change, right? Or % decrease. So what's the difference between X and Y? What's 15 minus 9? That's 6. And then we put that over the larger number, which is going to be 15. And what does that equal? Well, if we divide the top and the bottom by 3, we get 2/5. If we convert that into a percentage, we get 40%. So that's choosing numbers. But you can use algebra if you want to. I mean, you can really set up the algebra, but you have to be careful with the way you set up the equation. So remember, x is larger than y. So you have to say, okay, x equals y plus 2/3 y. And if you do a little bit of fraction simplification, you're going to see that x equals 5/3 y. Is that right? 3/3? Yeah, 5/3 y. And then if you move the 3 over, you now have 3x equals 5y. And from here, if you want to choose numbers or if you want to move the 5 over, so divide everything by 5, you'll see that 0.6, 3 divided by 5. I'm just converting it to a decimal, 3 divided by 5. So 0.6x equals y. So if 60% of x equals y, that means, oh, y must be 40% smaller, right? Because, of course, 60 plus 40% equals 1. So the correct answer here is B. All right, should we move on to number 7? Let's move on to number 7. The volumes of a right cylinder and cube are equal. So the strategy that I would use here is what's called piece by piece. And what I mean by that is stop. Don't move. Don't move on, right? Like, what does this mean? The volumes of a right cylinder and cube are equal. Okay, so what is the volume of a cube? If we say that the side length is x, it's going to be x cubed. Okay, what is the volume of a right cylinder? So we know that we have to take the circle on the bottom, right, which is going to be pi r squared, and then we have to multiply that by the height. Okay, so notice by stopping there, we can set up this equation and make sure that we're on the right path, right? So keep reading. If the height of the cylinder is 6, okay, so let's rewrite this. So now we have x cubed equals pi r squared times 6. And the radius equals the side length of the cube. Oh, okay. So if the radius equals the side length, we can say that x cubed equals pi. Remember, the radius equals the side length. So radius squared would be x squared times 6. And now we can divide both sides by x, or x squared. So if we divide both sides by x squared, remember, these are all positive numbers. There's no we don't have to worry about negative or zeros. So x cubed divided by x squared is going to be x equals 6 pi. Awesome. So we just found that out. What is the approximate surface area of the cube? So remember, the surface area of a cube is going to be 6 times the side length squared, right? We know that the side length is 6 pi. So the surface area is going to be 6 times 6 pi squared, which is going to be 6 times 36 times pi squared. At this point, I would just use a calculator and just using 3.14 for pi. I mean, we don't have to be that accurate. It says approximately. So 3.14 times 3.14 equals 9.8596. We're going to multiply that by 36, and we're going to multiply that by 6. And what do we get? We get 2,129 approximately, which is going to most closely match 2,130. So I think this is a really good candidate for the piece-by-piece strategy. Be careful with writing your multiplications with these dots. I mean, you can really easily confuse them as a decimal sign. I should probably use like an x, to be honest, but then you might confuse that with the variable x. What do you do? I don't know. Question number 8. How many positive integers less than 200 are divisible by 4 or 5? So before we tackle this problem, do you agree that some numbers are going to be multiples of 4, less than 200? Okay, you agree with that? Do you also agree that some of these numbers are going to be multiples of 5? Do you agree with that? Do you also agree, oops, that should be a 5. Do you also agree that some of these numbers are going to be both? They're going to be both a multiple of 4 and a 5. So what we need to do to find the answer is we need to add the multiples of 4, how many there are, to the multiples of 5, however many there are, and we need to subtract out how many multiples of both there are. And the reason why we're subtracting out is not because we're removing those, but we're removing the double counting. Because notice, whenever we find the multiples of 4, we're going to find these multiples of 4 and 5 as part of that process. Whenever we find the multiples of 5, as part of that process, we're going to find multiples of 4 and 5. So notice we're finding the middle area twice. We don't want to have it twice. We want to just have it once. So if you think about it as colors, so we're adding up this region here, only the multiples of 4, right? Plus only the multiples of 5. So this is where there's no overlap whatsoever. And then finally, we're also adding up what's in the middle. The problem is the middle's being double counted. So if we actually solve this problem without removing the double count, it would look higher than it is in reality. All right, so let's go ahead and solve this. How many multiples of 4 are there from 1 to 200? I know it says less than 200, but just bear with me. So from 1 to 200, how many multiples of 4 are there? Well, what's 200 divided by 4? It's 50, right? So in that case, there is 50 multiples from 1 to 200 of 4. But keep in mind, 200 is a multiple of 4, so we need to actually subtract that out. So there's going to be a total of 49. So 49 multiples of 4. Now, if you don't know that shortcut, whenever you're doing 1 to something, you can just divide the bigger number by whatever it is, the multiples you're looking for. That's kind of a shortcut. If you don't know that shortcut, you can use the formula, which is going to be the last multiple of 4, right, minus the first multiple of 4, all over 4. And then finally, don't forget to add 1. So if we actually do that process from 1 to 200, less than 200, what is the last multiple of 4? It's going to be 196. Remember, we can't include 200. Minus the first multiple of 4, which is obviously 4. We're going to divide that by 4, and then we're going to add 1. So what we have is we have 192 over 4 plus 1. 192 over 4 is 48. And then, of course, 48 plus 1 is 49. Okay, so we found the number of multiples of 4. We can do the same thing with the multiples of 5. So from 1 to 200, how many multiples of 5 are there? 200 divided by 5 is 40. But remember, we can't include 200. So that's going to be 39. So 49 plus 39 is going to equal 88. Is that right? Yes, 88. But we need to subtract out the double counts. This is the problem. We're double counting. The first number that's double counted is 20. 20 is both a multiple of 4 and 5. So we can't include that, right? Because we're double counting it. We counted it once with the 4s and once with the 5s. The next one is 40. The next one is 60. Notice that these are multiples of 20. So we need to subtract out the multiples of 20 to remove the double counting. So from 1 to 200, how many multiples of 20 are there? Not including 200. Keep that in mind. So 200 divided by 20 is 10. But remember, we're not considering 200. So the correct answer is 9. So what we have is we have 88 minus 9. And what do we get? We get 79. Is that the correct answer? Let me pause the video and look at the answer key. Hold on. All right, I just checked the answer key. Everything looks good. So let's go ahead and move on to question number 9. Number 9, if x is an integer less than 10, how many different triangles are possible? So this is, you could brute force this, I mean, to be honest. I mean, if you just want to say, okay, if x equals 1, does it work? So that would result in a triangle of 1, -1, and 5. So the answer is no, that doesn't work. If x equals 2, now this side equals 0, okay? That doesn't work either. If x equals 3, we have 3, 1, and 5. That's not going to work either because, remember, the sum of two sides has to be greater than the other side. So 3 plus 1 is 4, which is not greater than 5. So that's not going to work either. Let's try 4. So 4 plus 2, so 4, 2, is that greater than 5? Yes, it is. So that does work. And then we go all the way to 9 because, of course, less than 10. 6, 7, 8, 9. All of these are going to work. All of these are going to work. So the correct answer is 6. Now, that if we want to solve this algebraically, we know the sum of two sides has to be greater than 5, right? So we say, okay, x plus x minus 2, we get 2x minus 2 has to be greater than 5, which means that 2x has to be greater than 7. If we divide both sides by 2, x has to be greater than 3.5. Now, of course, there are an infinite number of numbers that are greater than 3.5, but there's some restrictions here. First of all, x has to be an integer, number one, and it has to be less than 10. So that only allows for 4, 5, 6, 7, 8, 9, which is 6. So the correct answer is D. Question number 10. Which of the following numbers consists only of digits that are multiples of 3? So this question is purely conceptual. And again, what do we mean by that? We mean there's really no math involved. It's really just testing your knowledge of something. And really what it's testing your knowledge of, if we break it down to its most base form, it's like, do you know that 0, here, we'll even write this down. Do you know, and I'll try to use good handwriting. I'll fail, don't worry. That 0 is a multiple of 3. That's really what this question is. That's all it is. Do you know that 0 is a multiple of 3? In fact, 0 is a multiple of every integer. It's a multiple of every integer. So if it's a multiple of 3, well, obviously 5 isn't, so that's out. 2 isn't, so that's out. These three, this one is definitely true, 369 and 699. But here, see that 0 right there? 0 is a multiple of 3, so we choose that. Now, you might be asking, wait a minute, why is 0 a multiple of every number? Think about it this way. Take, for example, the number, let's say 12. Can you divide 12 into two groups? Yes, you can. 6 and 6. So because you can divide it into two groups, it is a multiple of 2. And I mean even groups, right? Even groups. Can you divide 12 into 12 groups? Sure. I mean, we could do 1, 1, 1, 1, 1, 1, you know, exactly. So this is why 12 is a multiple of 1, because we can divide it into 12 groups. Or sorry, a multiple of 12, because we can divide it into 12 groups. So it's a multiple of 12. Can you divide it into one group? Yeah, 12. So that's why it's a multiple of 1. So here comes the question. Can you divide it into 0 groups? Sure. See, it's like, well, why not, right? We just do nothing. So that's kind of one way to think about it, right? So can we divide the, yeah, I mean, right? I mean, we can, right? Why not? So I'm trying to think if that's a good way to think about it. So again, let's take the number 9. Can we divide 9 into one group? Yes, just 9. Can we divide it into 3 groups? Sure. 3, 3, 3. Can we divide it into 9 groups? Sure. 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. So that means it's a multiple of 1, right? It's a multiple of 3, because 3 groups, 1 group, and a multiple of 9. Can we divide it into 0 groups? Yeah. Right? I think so. That's one way to think about it. Another way to think about it is this. If we do 9 times 0, we get 0, right? So yeah, 0 is a multiple of 9, because 9 times 0 is 0. Yeah, I don't know. Maybe I'm confusing myself, but I think this is a good way to think about it. If none of this makes sense, just remember that 0 is a multiple of every integer. Okay, so the correct answer is C, D, E. Number 11. So this is a simplification problem. The first thing that I would do is choose numbers. I think a lot of people's instinct here is to try to simplify the algebra or the roots. But what if we just say x equals 0? Does that allow us to eliminate anything? If x equals 0, obviously this is going to equal 0, and all of these are going to equal 0 too. Okay, so that wasn't very helpful. What if x equals 1? So if x equals 1, this is going to be the fourth root of 32. I don't think that's an integer. There's no number that if you multiply it together 4 times, you're going to get 32. No integer, I mean. So that means if we plug in the 1 into all the answer choices, this would be 2. This would be... Yep. So this is actually an interesting thing. So my first hunch is to choose numbers, right? But then when I start trying to choose the numbers, I'm realizing this is actually going to be quite time consuming, at least for this specific problem. So if I'm taking a real test, sometimes I'll shift gears and I go, okay, choosing numbers seems like it's going to be very time consuming. I just told you that's my first instinct, my first hunch, but it doesn't always work cleanly. So now let's actually simplify this. So if we simplify this, we can apply our radical rules, our roots rules, and we can rewrite this as the fourth root of 32 times the fourth root of x to the fourth. Okay, that's what we can do. Now, the fourth root of x to the fourth is actually going to equal the absolute value of x. See, here's the thing, right? Whenever you have x to the fourth, and then you have the fourth root, what operation do you do first? Do you do the fourth root or the fourth power? You do the fourth power. The reason why that's important is, watch what happens when I say x equals -1. If x equals -1 to the fourth power, isn't that positive 1? So it's like no matter what you do here, no matter what you do with x to the fourth, whether it's positive, negative, or 0, it's going to spit out either a 0 in the case of 0 or a positive number. The other way to think about that is it's the absolute value of x. So this is the absolute value of x. A more simple example, a simpler example would be the square root of x squared. Don't automatically assume that this equals x. It doesn't equal x because watch, if x equals -1, well, okay, -1 squared is +1. The square root of +1 is 1. 1 equals -1? No, that doesn't work. So that's why this is actually the absolute value. So anything that doesn't have the absolute value, I can get rid of. So let's get rid of this one, and this one. So now I just have to figure out what's going on with D and E. So that's when I need to simplify this part, the part on the left. So let's rewrite this as the fourth root of 16 times 2. That means I can rewrite this as the fourth root of 16 times the fourth root of 2. What is the fourth root of 16? That's 2. So 2 times the fourth root of 2, which of course is going to match with answer choice D. So the correct answer is D. So we started this problem, I started this problem with a choosing numbers hunch. And I found out that it didn't really work that well. Or maybe I just didn't apply it very well. In which case, it's okay to pivot. This is why we call it a strategy toolkit. Not something that you should be required to use at all times. Okay, let's go to the next one. Number 12, if y equals this, what is the highest possible value of y? Okay, how would we approach this one? It kind of depends. If you have a really good algebra understanding about how this works. So one thing you could do is you could multiply it out into the quadratic, right? So we have negative, and then if we multiply this out, FOIL, right? FOIL. So it's going to be x squared minus 8x plus 3, so minus 5x, and then finally minus 24. And then if we were to distribute the negative, we get negative x squared plus 5x, and then plus 24. So how do we find the highest point here? You could do calculus where you take the derivative, but of course that's not required on the GRE. So instead, let's think about this logically. Let's think about this logically. All right, so if we think about this logically, so we know that this is a negative quadratic, which means the parabola is going to be upside down. We know that it's going to intersect the x-axis at x equals 8, because that's what causes it to be 0, right? So x equals 8 right there, and x equals -3 right here. So we'll call that -3 right there. We know it's going to be an upside down parabola, so it's going to look something like this, right? The highest point is going to be right in the middle of these two x values. Right in the middle of these two x values, right? Or at least the x value is going to be, it's going to mark the highest point. So what value is in the middle of these two values? So what is the distance from -3 to 8? Well, that's going to be 8 minus a -3, which is going to be 8 plus 3, which is 11. So this entire distance is 11, an 11 distance. Remember though, we only want half of it. We only want half of it. So half of 11 is 5.5. So if you do -3 plus 5.5 because we're going to the right, or 8 minus 5.5 because we're going to the left, in both cases, you're going to see that this equals 2.5. Now notice, this is the x value. We want the highest y value. So in that case, you have to plug that in. Plug in the 2.5. So let's go ahead and plug it in. So we have y equals negative. So 2.5 minus 8 is going to be -5.5. And we're going to multiply that by positive 5.5. Notice how it created a perfect square, which makes sense because that's how you really maximize things with perfect squares. So we get a negative times a -5.5 times a 5.5. If you multiply all of that together, I think you get that one right there. Let me confirm that with a calculator. 5.5 times 5.5. Yep, that equals 30.25. So the correct answer is A. Now, is this the only way to solve the problem? No, there are shortcuts. You know, like I said, you can do calculus. You can take the derivative. For anyone who doesn't understand what I'm talking about, ignore this. It doesn't matter. It's not important for the GRE. But for example, you could take the derivative of y, which is going to be -2x plus 5. You then set this equal to 0, so -2x plus 5. And what you find out there is that x equals 2.5, and that's exactly what we found out. That's exactly, now this was faster, but you have to kind of know derivative rules and how it works and all that stuff. Again, if that sounds like Greek to you, it sounds like crazy, just ignore all that. Question number 13, what is the greatest number of non-overlapping obtuse central angles that can fit in a circle? This is one of these questions that you first have to even understand what the hell they're talking about, right? So I'm going to pause the video. I'm going to create a graphic. All right, so we have this circle, right? And of course, the central angle is going to be from the center. So first of all, we need to set these up like right at the center of the circle. So here's one of these. There we go. And then this is an example of a central angle, everybody. Right there. Okay. But the rule is this central angle has to be obtuse. I lost my marker. Here we go. So this central angle has to be obtuse, not stupid, not that definition of obtuse, but the angle. And an obtuse angle is going to be one that is greater than 90 degrees, not equal to 90 degrees. So greater than 90 degrees, but less than 180 degrees. So again, you could just choose numbers here. I mean, okay, let's imagine we're just saying the angles are 91 degrees. I mean, how many can we fit? How many can we fit? So 91, and then if we have one of them, it's 91 degrees. If we have two of them, it's 182 degrees. If we have three of them, it's going to be 273 degrees. If we have four of them, it's going to be 364 degrees. obviously 4 is not going to work because there's only 360 degrees. So that's out. So we can definitely fit 3 in there for sure. Now you can say, okay, what if we do like 90.0000001, for example? Just we don't make it equal to 90 because an obtuse angle cannot equal 90, but we make it as small as possible. In that case, you're still going to have the problem because it's still going to be like 360.0000004 or something like that. It's still going to be greater than 360. So you cannot fit 4 in there. Another way to think about it is, how many right angles can you fit? How many 90-degree angles? You can fit 4 90-degree angles because 4 times 90 equals exactly 360. But if any one of these angles is slightly larger than 90, it all breaks it apart, right? In that case, you can't have 4 obtuse angles. You can only have 3. So the correct answer is C. Question 14. Which of the following represents the complete set of x values that satisfy the inequality below? You could solve this conceptually and go, okay, what kind of x value is less than x cubed, but at the same time less than x squared? And you could kind of try to fool around with it. You could maybe even try to do some algebraic rules. I personally wouldn't take that approach. I'm not saying your approach is terrible or anything, but for me, I just think it's so much easier to choose numbers. Let me show you what I mean here. Okay. What happens if I choose a positive number greater than 1? Okay, a positive number greater than 1. I'm going to choose 2. All right. Does 2 work? So 2 is less than 8. 8 is less than 4. No. So anything that includes numbers greater than 1, I can eliminate. So I can eliminate this one. Not super helpful. Not super. I got rid of one of them, right? It's not too bad. It's not too bad. Okay. What if x is, let's say, equal to 0.5? So x is equal to 0.5, which is a positive number greater than 0 but less than 1. Okay. Does this work? So this would be 0.5, which is less than, what's 0.5 cubed? Let me take a look. So 0.5 times 0.5 times 0.5 is 0.125. Does that work? Is 0.5 less than 1 point? What? Does that? No. So anything that has values that are valid from 0 to 1 is out. So this one is out. This one's out. Okay. And then we say, okay, what if I say x equals -2? Right? So this would be -2 is less than -8? No, -2 is greater than -8. So that is out as well, which allows me to eliminate this one and this one. So the correct answer is D. So just using a little process of elimination, that's probably how I would do it. Now, would I stop here or would I confirm? No, I would confirm this for sure. I would confirm this. So take, for example, if you plug in -0.5, which is valid in this range, does it work? So let's see. So we would have -0.5, which is less than a -0.125, which is true, which is less than a positive -0.5 squared 0.25, which is also true. So it works out. So the correct answer is D. And we are about to end this journey, everyone, with our last one. If the longest diagonal of a cube A is 5√3, stop, piece by piece method, right? Okay. If your conceptual foundation is very strong, you'll know that the longest diagonal is going to equal √3 side, which immediately allows you to say, oh, in cube A, the side length equals 5. And you could do the same logic with B. In B, the side length equals 8. But of course, you have to have a pretty good foundational understanding of how that works. If you don't have that, obviously you have to work backwards, which makes this problem a little bit harder, to be honest. So this is why we say it's so important to memorize this stuff, just to kind of, if you have this stuff memorized, you can solve the puzzle part. And what is the puzzle part? All right, so here we go. If A has a side length of 5, what is its volume? Its volume is going to be 125, right? 125. 5 times 5 times 5. That's the volume. If the side length of B is 8, it's going to be 8 times 8 times 8, which I think is 8 is 2 to the 3, right? And we're doing that 3 times. So this is going to be 2 to the 9th, which I think is 512, if I'm not mistaken. We could also find the surface area here if the problem asks us to find the surface area. I don't think it does. It's asking us the difference in the volumes. So we're going to do 512 minus 125, and we get 387. So that's it, everybody. That is the section 2, 15 questions. I hope you guys enjoyed that. And I'll try to put more of these out there so you can practice your quant and listen to me talk about math if that's something that you're into. I don't know why you're into that, but if that's something you're into, then maybe I'll put more of these out on YouTube. Let me know in the comments if this is something you want me to keep putting on YouTube. Just let me know. All right. And if you guys are looking to boost your foundation, this is where maybe I can do a plug for GregMap. If you guys are looking to boost your foundation, $10 a month, you get GregMap Plus and PrepSwift, and you can, with that subscription, you can join what's called the I'm Overwhelmed plan. And the I'm Overwhelmed plan really does a good job of building up your quant foundation so that these problems, which I'm not sure, are these medium or I'm not sure, I'm going to find out. These problems are going to seem a lot easier once your foundation is really, really solid. All right, that's it. I hope you guys enjoyed this. Again, let me know in the comments if you want me to put more of these on YouTube. All right, everyone, I hope you guys have a wonderful day. All right, talk to you later. Bye.